Okay, good morning. It's time to start the keynote session. It seems that we'd better to wait a few more minutes. Before we start, I have a small announcement. Yesterday, somebody left these glasses. I'm looking for the owner. It's yours, okay. Okay, my name is Un Tae-gu from KAIST in Korea. I am session chair of keynote speech. Welcome to the second day keynote speech session. Today's keynote speaker is Marchal. She is already well known, and I don't need to introduce her, but I briefly introduce her previous activities. Currently, she is a professor at University of Rennes. And also, she is involved in several activities, especially PI of the ERC. Also, she is very active in organizing related international conferences, including ISMAR. She is also in charge of the steering committee members of ISMAR. Also, she served as PC chairs of related conferences like haptics, Eurographics, VR, etc. Yesterday, we already learned how much important, I mean the importance of the multimodal interfaces, especially the haptics is pretty much key component of a multimodal interaction. Today, she will introduce the haptic modality. Her topic is exploring novel haptic modalities with a mixed environment. Let's welcome Maud.
You want your phone? You want your phone, Monta? So thank you for the kind introduction, and good morning, everybody. So it's really my great pleasure to share with you my interest for sense of touch and to explore with you how we could design haptic feedback within mixed environment. So I have been interested in haptics since almost the beginning of my research work. So this is my first haptic device I did like 20 years ago during my master thesis. And as you could see, this is a very nice homemade tracking system, already a wearable device, and only 1 degree of freedom at that time. And what was this device for? So it was, in fact, for teleechography. So it was for a telegraphy robot so that the physician could have feedback on the vertical axis when he was exploring the patient with a probe. And this device was presented in a conference called Medicine Meets Virtual Reality. And we could observe at that time a switch in the community, haptic devices being mainly used for teleoperation purpose and started to be used also for VR applications. And to better understand the main challenges behind the design of haptic feedback for mixed environment, let's first redefine a little bit what are the specificities of haptics and how we could handle together during this presentation like the challenges for the design of haptic feedback. So haptics is related to our sense of touch, and when you put a S of haptics, it's come to like an international scientific vocabulary, and it comes from the Greek haptikos, and it has its own research community since almost 1 century. And in the haptics community, we are like studying like the diversity of haptic stimuli that we have in our real life. So when we are like feeling like the diverse haptic sensation, like manipulating objects, instruments, or materials. So we have already like a diversity of haptic stimuli, and we usually divide the haptic sensation into 2 groups, different groups, cutaneous and kinesthetic sensations. So kinesthetic sensations are related to the forces and couple in our muscles or joints. For instance, when you hold a glass, the gravity force produces a kinesthetic sensation in your arm. On the other side, like cutaneous sensations are felt thanks to the mechanoreceptors that we have under our skin. So these receptors are present on the whole body, and we can feel vibrations, textures, or temperature, for instance. So here, for instance, on this example, you can feel if the liquid is hot or cold in the glass with your cutaneous sensations. So as we could see, and as we know in the haptic community, we are experiencing various stimuli in our daily life. And the main questions that come to our mind, if we'd like to introduce this in VR, is how we could handle this diversity when manipulating objects in VR. So when we like to manipulate a VR object, most of the time we are using mirror interaction. And also we have like considerable progress these last 2 decades for interaction in VR. We are still lacking haptic feedback and missing like convincing sensation for haptics. So we have all experienced the manipulation of objects where we can interpenetrate the virtual content, reducing both the realism of the interaction, but also breaking the immersion sometimes. So compared to the other sense, haptic feedback still really miss convincing sensations. So thanks to the nice picture of my PhD student, we can see that diversity of haptic stimuli is therefore like still poor when interacting in VR. So I will use this cat picture during my presentation to show like, yes, we would like to have a cat, but yes, we have a sort of cat at the end, but still we don't have exactly the cat that we would like to do. So in my presentation today, I would like to illustrate some of the challenges that have been handled this last decade, and what are the next directions that we have to handle for, and we have to address for having this nice cat at the end. So I tried to summarize like the main challenges for designing haptics in VR with this picture. So here you have like a user on the left side, and then you have on the right side the virtual environment. And in between, if you'd like to have haptic feedback, then you need to use a haptic interface. So it could be one interface or several interfaces, depending on where you would like to put haptic interfaces on your body. I will come back to this later. And then on the green part, so you have like the haptic rendering scheme, which will couple the haptic interface to the simulation and the virtual environment. On top of that, because like we are doing several different types of interaction in VR, we could also use and design interaction techniques that will take some software and hardware components all together. So we have several challenges here, and I would like to propose 4 different types of challenges today and try to discuss these challenges. The first one is our knowledge of the human haptic system. So the sense of touch is complex. It involves sensation on the whole body compared to visual feedback when you have like only eyes, or audio feedback when you have only ears. And we have knowledge coming from the haptic community, but we still have the remaining question about like the exact mapping of users' haptic perception in VR compared to the real world. So this is the first challenge that I would like to discuss today. Then second challenge is about the design of the haptic devices suitable for interaction. So we have observed this last decade like the emergence of novel tactile technologies, especially using 3D printing devices. And these devices explore the sensation on the whole body instead of like the classical kinesthetic devices used for teleoperation purpose. And this, of course, enriches the different type of stimulations that we could have at the hand, but still it remains how we could design the best devices for having like the diversity of haptic sensation we already have in the real life. Then third challenge I would like to talk about today is the simulation of the virtual environment, especially the virtual proxy, which means like the representation of the user in the virtual environment, and how we could interact with virtual objects. As well also like in here we have like the coupling schemes that we would like to handle and to address. So rendering haptic feedback is like very challenging in terms of computation time performances, since we need to generate a feedback at a frequency much higher than for visual or audio feedback. So for a contact, for instance, we have for an object, we need to render it at 1 kilohertz to be felt as in the real world. And of course, this is much higher than for visual or audio feedback rendering. And then the last category of challenge I would like to speak about today is interaction techniques, which combine hardware and software elements to allow a user to perform specific tasks as to be considered. And we need to explore how, with this interaction technique, how we could manage somehow like to have this different type of interaction, and how we could somehow try to map or not this to what we have in the real world. So I entitled my presentation Exploring Novel Haptic Modality within Mixed Environment to highlight the fact that the haptics in VR is nowadays still a real adventure. We are still exploring a lot of different directions of research. And in the rest of my presentation, I would like to show some illustrative example of these challenges I presented here, and then discuss a little bit about some perspectives that we could have in the community all together for designing haptic feedback in mixed environments. So to focus a little bit the discussion and also the different illustrative example, I will in this presentation I will do a specific focus on bimanual haptics. So why bimanual haptics? So here you can see a few actions that you probably perform quite often in your daily life. So one common thing that this task is like most of the time they are performed using our two hands. And for instance, one hand can be used to hold something and serve as a reference point so that the other hand can achieve a manipulation. And another interesting thing when you look at this action is that this manipulation would be much harder without haptic feedback in our real life. And then, of course, when we come to VR and how we could introduce haptic in VR, we have to think about how we should map this bimanual task that we're handling in the real life to VR applications. So we like first to try to illustrate some of the challenges with some of the contribution we did this last year. So let's start with the software challenges. As I said, computation time performances are one of the key limitations as of today for complex haptic feedback rendering. So let's illustrate this with an example of bimanual haptics. So when it comes to bimanual haptics, let's think again about our cat. So we need to simulate the cat, but also we need to simulate the hand who will touch the cat somehow. Otherwise, I mean, you will have less experience with your cat. And how we'd like to simulate the hand, we'd like to know what type of simulation we could do. So by nature, hands are deformable. So of course, we like to have this. But most of the time, when we are using VR hands, we are representing this hand with rigid objects. And even in a more simplified version as rigid proxies. And in fact, our choice here for choosing the hands that we'll use for simulating and interacting with the virtual environment, our choice is like dealing with the trade-off between realism and computational time performances, because on one hand, you have deformable model, and then they have the most realistic on one side, but the rigid proxies allows like I would say rapid prototyping and manipulation within virtual environment on the other side. So one of the main constraints that prevent for using the deformable each time we would like to interact with the environment is, of course, the computation time performances. And the people try to find some solutions and some models that could be improved in terms of computation time performances to handle all these contacts that we will have with deformable objects. So deformable object, and especially deformable hand, it could be quite interesting for manipulating virtual objects. So the advantage of having a deformable hand is that you have a deformable finger pad, and that the contact surface is increased at initial contact, which makes the resulting grasping more stable. So the main challenge here is the increasing number of contact points, making computation more intensive. And one of the main issues that we need to address here is to keep this information of contact while being able to compute it fast enough so that we could have realistic haptic feedback. So one of the main challenges in the community today is to propose novel solutions for improving the computation time performances. So I will illustrate this with one of our contributions that we did, where we try to formulate and try to aggregate constraints for the simulation of dexterous grasping. So when you deal with a deformable hand, so you need first an input, and then you need other components, physics-based simulation of your hand. Then you need, of course, a hand. So when you have a deformable hand, you don't need to have a full deformable hand, depending on with which part of the hand you would like to interact with. You can have only articulated rigid body hand, and then for the deformable part, then you could have a deformable model, like, for instance, finite element methods is the one that we used. And then, of course, in addition to this, you need a visual model and a collision model so that to be able to have the physics behind that would behave correctly for the contact. And of course, it means that we have a lot of different components, and each of these components takes time, like a lot of time for some of these components. And then we should think about how we could decrease these computation times. So what we need to deal with is like you have mechanical phenomena that are quite well known in the physics community, and then you need to somehow trying to translate that then in the virtual community and the computer graphics community so that you are able to simulate dexterous grasping. So for these formulations, we try to simulate two different mechanical phenomena very precisely. First one is a non-uniform pressure distribution. So here you have a scenario of grasping a cube that showcases the importance of pressure distribution in our contact model. So uniform pressure over the contact does not allow you to grasp object from its edge, as for rigid finger. So this is, for example, the case when you can see robots trying to grasp objects and it slips. It's just because of the contact surface on this object. On the other side, when you await the contact point within the aggregate constraint, it will restore the pressure distribution, allowing the cube to be lifted, like this, for instance. So we try to formulate this with the constraints, and then I will skip, of course, the equations today. And then we also try to think about friction. Friction is quite important. We like to manipulate objects, and we added to the classical Coulomb model for friction, a torsional friction model based on the Coulomb-Contenson friction model, and our model proposes both the friction force and torque at the finger in contact. As you could see on this video, when you are grasping an object from one with your two fingers, and the object will stay in a horizontal position with a given pressure, and then if you release a little bit the pressure, then you will be able to rotate your object with your finger, but still you are not releasing fully the object. So with these two components, then you are able to have quite some nice grasping dexterous scenario. And this is some example of the results. So here you have a full hand simulation and for the grasping an object. So as you could see, this is interactive, and we can reach a frame rate that is compatible with haptic feedback. So we divided by 10 years the number of constraints compared to a classical approach. And then the simulation time was decreased about 60% at the end. And of course, because we are in Biermann scenarios, and you increase of course the computation, but still here we decrease the simulation time by more than 30% on this example. And then you can have dexterous manipulation also, I guess this one you are using it when you start to be bored, like spinning your pencil with your finger. And as you could see on this example, we have been able to manipulate both with this friction model and rotation, but also with the non-pressure distribution that we have under our finger, this type of dexterous manipulation in VR. So this is a first example of what we should deal with when we like to manipulate a deformable object and trying to have at the end haptic feedback with this deformable object. So sometimes when you look at the simulations, then you need to look also at how you would like to link this with the haptic interface you are using. And the simulation of the virtual environment should be made in accordance to the haptic rendering method you would like to have. So for instance, while the method I just presented significantly improves the computation time and the contact constraint resolution, the simulation of the hands that I presented, like all the models that you have seen, still is very expensive in terms of computation time. So we could think about alternative to a fully physics-based simulation, and this comes to improve and to present new haptic rendering methods. So to handle contact rendering, we could, for instance, try not to use a fully deformable model, but trying to use rigid model, and it could be quite an interesting alternative to deformable model. However, we'd like, with this rigid model, being able to keep these contact surfaces, as explained before, because these contact surfaces that soft model provide are very important for grasping and stability of grasping. So we could have a heuristic approach for this instead of physics-based simulation. And for instance, here is an example of what we could do if we have this type of approach. So the idea is you would like to have a rigid model, you would like to have your surface rendering under your finger, and then you would like to have everything here in your simulation. And so what we propose is what we call the God figure method related to the God object approach that has been introduced in the haptics community. And when you would like to think about the propagation of a contact surface from a contact point. So you have two main points, two main steps for this one. First is like you'd like to generate with a fingerprint where you have the contact on your object, and then you would like to fit your fingerprint on the object and trying to propagate whatever the mesh of your object is. So if we go a little bit into the details, then you can see that with your fingerprint approach, you would like to guide the propagation depending on the mesh. Of course, you don't have always like a planar surface for your fingerprint, and then you have the contact surface that could be simulated quite easily. And for that, you have like a local geometry scan for doing this, and it can be used whatever the surface is, like concave or convex shapes could be used. You just have like to have like a threshold for doing the propagations. And this could be implemented in haptic rendering with like a 1 kilohertz rate, like compatible with haptic feedback. Example here is like when you have like the initial like contact model and rigid model. Here with this ball, you can see that sometimes it's not so easy to manipulate this sphere. When you are using some heuristic approach like the gut finger approach, for instance here, but you can have like more stable contact and manipulation. So it works also when you like to lift objects, for instance. If you have only one contact point, you are not able to lift any object. And of course, it also works when you are using bimanual scenario, because we were speaking about bimanual scenario since the beginning. If you are using rigid model, like with one contact point, of course, you are not able to grasp, as I presented before, with the deformable hand. And so with this approach, then you have the contact surface that is preserved, and then you are able to grasp the object. So we could see with this type of challenges that the design of the haptic rendering method is also important in addition to the choice that we are doing in the simulation. So we are not like, it's not like mandatory to have like a fully very complex physics-based model. I will talk to this later. And we could use like haptic rendering approach for handling all these phenomena that we like to handle and to simulate in the environment. So on top of that, once you are able to grasp, then you have other type of interaction you would like to do also when you are manipulating objects. So when you manipulate objects, and for instance, when you manipulate a bimanual object, we would like also to be able to navigate with them, being able to grasp and sometimes not grasping. And when it comes to bimanual scenario, I will present here, it can be quite painful when you have like two different type of interfaces, so just for the purpose of explaining what is handled here. And here you are clutching, and of course you are not clutching, that is the same with your two hands, so sometimes it could be painful. And when you like to grasp at some points, of course you are not fully aligned, and then you cannot grasp the object, especially when you have your two interfaces. And at some point, you have your left interfaces, which is on the right part in the environment, and then you start to feel that bimanual grasping will be just impossible. And it's here when you can, you can also introduce, in addition to the classical haptic rendering methods I have presented before, interaction techniques. And for instance, I will illustrate this with what we call the bubble mechanism. This is a technique that allows to explore how we could manipulate virtual objects in the virtual environment. So it's based on the principle of bubble, the bubble metaphor proposed by Marchal, but you use it for a double bubble. So the principle is when you are inside the bubble, then you are in a position control scheme, and when you reach the limit of the bubble, then you start to be in the height control scheme. And this allows you to explore the environment when you are moving your interface. And then it comes when you like to have two interfaces, then you need two bubbles, but still you need to handle how you like to manipulate and to use these two bubbles simultaneously. So it works well, and then we need to, as I mentioned before, like with the limitation in the previous video, then you need to handle also these two bubbles working all together and having this bubble that could be able to cross, and how we could handle this. So I will go a little bit into the details of some of the components that we did for this double bubble metaphor. First thing is you need to adapt the viewport. So we need to keep the proxies in the field of view for both bubbles, and then we need to adapt the viewport. So what we did is for translations, when we are translating in the environment, that you can adapt the bubble position and width, and you will have the viewpoint that will be positioned at a distance to the center of the scene, depending on the position and width of the two bubbles. For the rotations, we are doing like a substitution of height control to translate to have like translational velocity that will be substituted to angular velocity. And if you don't want like to sacrifice the degrees of freedom as we are doing like this, you can also use like a separation plane as a revolving door mechanism, as you could see here on the video. So this allows you to explore the environment with bimanual application and your two devices, and then of course adapt your view and your viewport on what you are doing. Then at some point, you would like also to grasp the object. So for that, you have two bubbles. If you are using like two different bubbles, of course, it could be like quite painful to manipulate them because one will be able to be in a position control mode, and the other one will be in a height control mode. And of course, this is not really easy to manipulate when you have like you don't have like a symmetry between your two hands. So what you need to do is like having same bubble size and also same height control velocity for your two bubbles. So what we did is implementing like bubbles and also trying to manage average velocity to be able to manipulate objects and grasping them. So we come to grasping, and when we like to grasp, of course, you need also to introduce like an interaction technique for grasping. And for this, what we use is we use the forces coming from the interface to apply on the object, plus the relative position of the hand, and we try to have like a force threshold of the hand, so that like we could like do like a way. We could with a recast, like for instance, with both hands trying to detect when we will try to grasp the object. And in addition, we had like a visual haptic magnetic pinch when grasping the object, as you could see here on this video. So this is some example of what you could do when we like to design interaction techniques in top of what you have for interacting with your environment. And of course, each time you are like introducing a new interaction technique, you need to do user studies. So I did not like spend a lot of time like speaking about user studies before, but of course this is mandatory for all the applications and all the interaction techniques we are introducing. So for instance, for this one, for the God finger, we did one user study about pick and place. We did other user studies, but one was pick and place. And just to illustrate here, when you are comparing the different techniques, and of course you need to compare the different techniques to be able for this type of interface to know which one was the best one. So for here, for instance, what you have is you have like a control only, like you are clutching, compared to exploration only, so only the double bubbles and only the magnetic pinch all together. And you could see the red part is when you have all the technique together, and of course you improve both completion time and the number of objects that have been dropped. So with this type of things. So now if I come back to my picture from the beginning, so we have like a simulation in software challenge, we have like interaction challenges, and then at some point it comes to the question of what type of interfaces we could use. So as you have seen, so we have like a generation of kinesthetic haptic devices that have been used since several decades. And these haptic interfaces, of course, provide forces. It's what we would like to have when we are manipulating objects. But for some of them, they are not very intuitive for doing some gestures, especially when you like to grasp objects, for instance. So instead of using the classical haptic device, we could also think about trying to introduce interaction paradigm and trying to introduce other type of haptic device that are not providing force directly, but still combined with the other sensory modality, we will be able somehow to have like haptic feedback when, for instance, grasping objects. So I will illustrate this design of interaction paradigm with one metaphor that we did. We called this metaphor the virtual mitten. And the context what we like to have like object manipulation. And it's based on our observations that we can reproduce a lot of our everyday life objects we can reproduce a lot of our objects, like for instance here we have here when we wear a mitten, as we do not need our fingers for doing a lot of different tasks, as you could see here. And this is true for either unimanual or bimanual scenario. And as you could see here, like my PhD student did a lot of different applications. You can see on these different scenarios where you don't need your finger to do this task. He's doing everything with the mitten. So we could say, okay, could you use this paradigm and trying to use this mitten paradigm and trying to find somehow a trade-off between the too expensive and complex haptic glove on one side and the generic metaphors that we could use on the other side that do not always reproduce the natural dynamics of grasping, like when you are using a controller, for instance. So this is what we propose. This is virtual mitten. So I will go just a little bit into the detail of how we would like to implement this type of interaction paradigm. So here for our virtual mitten, each hand holds an elastic device to control a corresponding virtual mitten. So this device is very cheap. You can find it like if you like to have like some more muscles in your hand. And then you have like it corresponds to a virtual mitten in gray here in this picture, and you like to grasp object in a bimanual scenario. And the grip force applied by the user is also measured to generate pseudo-haptic feedback. So if we look a little bit into the detail of the components, so here the grasping on an object and the following interaction depend on the grip force applied on the elastic device. And then due to its internal elasticity, our device will provide like a passive force feedback. So it's really a passive device, not actuated at all. And then it enables the perception of effort, and it will be converted to perception of stiffness. So the virtual mitten is associated to a control scheme that will allow the user to control the mitten, representing their one hand. And here we propose an approach, still, this is an interaction paradigm, to reproduce the dynamic of grasping. So we have a first threshold that you could see here, that this threshold will be to select the object, and then we have another threshold which will be used for grasping and to formalize the grasping condition. We added like a progressive visual feedback composed of different colors that we evaluated in user studies to inform the user about the different thresholds. So in order to perceive different level of effort, we added also a pseudo-haptic effect on this interaction paradigm. Our pseudo-haptic approach is related to the evolution of the grip force when grasping an object. As you could see here, we are trying to, we have different type of thresholds that we introduce. So this threshold could be modified in order to accommodate the pseudo-haptic effect. So we performed a user study to assess the performance of the mitten, and especially we did a psychophysical test, and we found like 4 different levels of efforts that could be perceived for a basic screwing task with these mittens. So of course, this is very interesting, because coming back to our bimanual scenario, then we are allowed to grasp an object. So this is, for example, the case here in this fruit-o-matic scenario. So here the goal is to prepare fruit juice with a blender. So users are provided with 2 elastic devices so that both of the hands can interact with the virtual environment. And then you have various virtual objects that can be grabbed and moved around with a mitten. So fruit, the lid of the blender or glass, and fruits can be squeezed above the blender to extract their juice. And because we have different level of effort, each fruit has a different internal stiffness and will require a different amount of effort to be pressed. So then we have like these different food. For instance, here you have the bananas, and you put everything all together in the mixer, and then you have a dial that could be turned to mix the juice. And finally, you have a lever that you could pull to pour the mixed juice into a glass. So as you could see on this scenario, we are able to grasp a lot of different objects with different shapes and still having an haptic feedback just using this very cheap device, complemented by our interaction paradigm. So here you have your glass. And then we extended this, like instead of using this elastic device in your hand, you can also do the same with the finger. And then you can have multi-finger extensions, what we did with what we call elastic glove. And for this, then you have like different level of stiffness that you could use for manipulating objects, like for instance, medical palpations or for piano scenario. So here we have like some example of what we could do in top of haptic rendering methods, simulation, interaction challenges, and at the end, providing haptic feedback to the user in VR. So I would like now to do like some perspectives. So first perspective I would like to handle is the user's perception. So I did not speak for the moment about like the force challenging, the human aspect. But the human aspect is really fundamental when we are dealing with both VR and haptic feedback. So the role of the user is a key component. So I would like to underline that the we need to conduct user studies each time we are trying to introduce new paradigm, new interaction, new rendering methods to evaluate the user's perception. And I know that the community is doing a lot of effort this last year to improve the experimental design, and this is great, and it has to be followed. And of course, diversity matters, especially when we have haptic feedback. As you could see, we have a wide diversity of sensation in our whole body. We are not feeling exactly the same in our whole body, but also we have a wide diversity of sensation compared to other humans. And so we really need to handle and to conduct user study with diverse participants. We need to collect both quantitative and qualitative data to assess the user's perception, but also to better understand it in the context of VR and AR scenarios, because it remains this question about, do we feel the same haptic sensation in VR or AR compared to what we feel in the real world? And we are not sure about that, so we need to collect information. Yes, so data collection is ongoing, but we can't for the moment plan the user's perception, especially for haptic feedback. So could machine learning be used? It might be useful in the future, but for the moment we don't have adequate data, especially for haptic perception in VR. So it's still an ongoing question for the future, and we will see how it could be improved. I would like also to underline that we have differences depending if we'd like to implement haptic feedback in VR or AR scenarios. We really don't have the same sensation in VR versus AR. So we did some user studies this last year and some experiments about specific sensations, such as, for instance, stiffness or texture roughness, and we compare VR and AR scenario exactly with the same conditions, and we have differences. We don't feel the same texture, the same feeling, and we don't have the same feeling in VR and AR, and we should be very careful depending on what we would like to apply our technique for. At the end, I have a perspective for this key role of the user. I like this last perspective is the diversity of the user, because as this diversity is very wide, we could use our own body as a haptic device and trying to have it as a tangible for 3D interaction. It has already been proposed in the HCI community, but then now when we come to AR specifically, we can use this device and having it as a tangible for haptic feedback, as we have a wide diversity of haptic sensations that we could have on our own body. So this is like some perspective about the first challenge about human perception. And then for the software components, I have often been asked, why are you implementing physics-based environments? It's so complex and time-consuming, and this is true. It takes time, it takes a lot of time, and it's more difficult than using just on-the-shelf solution with rigid objects. So, as you have seen in the presentation, you have some great alternative to physics-based virtual environment, and they could be used, and this is what we are doing for most of the time. But still, for some cases, we need to have physics. And, oops. So this is, okay. So this is the case, for instance, if you are manipulating only solid objects only, then you don't need really like very big scenarios with a lot of physics. But you like to mix several material properties, such as deformable objects or liquids. It comes to a certain point when you need somehow a common framework for animating your object and manipulating physically. So this is the case, for instance, with like this scenario of virtual crepe that we did. So you have like a bimanual scenario still, and a crepe is like a specialty from Brittany, where I am from. And so for this scenario, you are manipulating liquid, and you are manipulating deformable objects, the crepe, and then you are manipulating solid objects, the pan, for instance, or the ball you are manipulating. And for this example, what we propose is to have like a haptic model based on SPH formulation. SPH is a smooth particle dynamics formulation. It's a particle-based simulations. And with this, we have like a common framework for simulating both deformable, rigid, and liquid objects. So we are able to manipulate deformable object and liquid. For instance, here you have like 6 degrees of freedom haptic interaction, like and you have like both force component and the 3 degrees of freedom of interaction. And then, of course, with this, then it comes to showcase this with a scenario of the virtual crepe cooking, and this virtual crepe, the user can pour some batter, a high viscosity fluid, from the bowl into the pan. So here you have like a framework that it is compatible with haptic feedback, of course, then you can pour and you can put a lot of butter inside or outside the bowl. And then at some point, you can feel the force and torque when you are pouring, but also with the weight when you are shifting between your hand, the batter, to go to the pan. And then once you are on the pan, then you can cook it, and then you have a deformable crepe. So this is like a very fast cooking stuff. And then when you have a deformable crepe, then you can put on it like maple syrup or salt butter caramel, which is also a specialty from Britain. So this is an example where we need physics. We have also some other example when we need physics, and it's especially the case when you are handling multisensory feedback. Because we need to somehow to synchronize the modalities. And using physics provide like a common framework for synchronizing the different sensory modalities. So using the same model as I presented before, we did multisensory rendering of fluids. So we have the particles, and once you have the particles, then you can create bubbles. And once you have bubbles inside the fluids, then you have the audio. So the sound is coming from the bubble when you are interacting with the fluid. So once you have the audio model, then you have the same equations for vibration. We are sharing the same equation for audio and vibrations. So we have all our model. And it allows us to do like some very nice multisensory feedback. And for instance, here you will have like a scenario for a foot floor interaction. So here the user's feet is under like vibrotactile transducer, and you have a full floor of vibrating tiles. And the user could walk on it and, for instance, stand here and experience wave washing up on a sandy beach. So you have like visual plus audio plus haptic feedback, and you have a kinesthetic feedback. And then we could also handle kinesthetic feedback. For instance, here, like you have a multiple degrees of freedom force feedback, where you have like a kinesthetic force plus audio plus visual rendering, and still at an interactive frame rate. So this is a case where we need physics if we like to have and to introduce haptics. And then a last example where we also need physics is for some applications. So where people from like the medicines or for robotics are coming and would like to do some application, of course, we need to have somehow physics. So one example, just to illustrate this, is like I did a collaboration recently with robotics people, and they asked us to do simulation, like full simulation, just to have data available so that they know how their robot could be planned in advance in an unknown environment. And of course, here you have a robot, so you need somehow to handle the physics of this robot. You would like to reproduce then the same action in the real world. So this is some perspective of what we could do for the software challenges. So if we come to the hardware challenges, of course, we have a lot of opportunities. As I said at the beginning, we have seen this last decade the emergence of a lot of tactile technologies that you could put on all your body. And I am like very enthusiastic to see and to participate to the design of the next generation of haptic interfaces. Not wearing the haptic device provides, for instance, some freedom to the user. This is the case, for instance, with this hand-coated haptic device that we have. And here we call this device a Vitavix. And this is a wearable device that we designed. And here you have the contact and the haptic feedback with the virtual object only when you are like in contact with the virtual object. So you can see it in the video. So here you will have the sphere that will come into your hand only when you are manipulating a virtual object. And we show, I will not show like the full video, but we show in this device that we could manipulate different shapes only using this sphere, and people were not able to feel the difference, and they are able to grasp the object only on demand. And of course, because this is a wearable device, it allows us to putting a HMD on the head and then being able to have like a freedom for the user. Another option is also like touchless devices, such as ultrasound, for instance, devices, because they are quite interested when we would like to manipulate objects. But these devices are array and they are fixed. So what we propose here, for instance, in this device is like to have like a robotic device on top of the device, and we are able to manipulate objects in VR, wearing a HMD and not seeing our real hand, and then having haptic sensation with this ultrasound device. And finally, there is also some nice opportunities when using 3D printing, and you can diversify your interfaces. This is the case, for instance, when you can introduce deformable materials in your device, like we did here in this tangible, for instance. So in this work, so what we did is we try to locate the tangible on users' equipment like wheelchair or walkers, so that people with disabilities were able to do some scenarios, and then were able to have haptic feedback during their training for navigation purpose. So when we introduce this haptic device, of course, we need to think about the hardware part, but the software component is really important. So we need to adapt or redefine the haptic rendering methods. Coming back to my bimanual scenario, and what we try to do with the middle haptics and middle ultrasound device, then we need to think about having also all the haptic rendering coupling schemes that should be resync. And for instance, here, when you are touchless scenarios, then you don't have any more contact with your objects. So you don't have collisions. So then you need to think about how you could redefine the signals that you would like to have for your user. So this is example here, for instance, for the pottery. And then, of course, it works well for other scenarios, and this is where touchless scenarios are interesting. So this is, for example, a concertina. It's a specific instrument. It's supposed to do some... And of course, here you have the feedback of the music is coming with the touch sensations, and then you can modify your movement with the haptic feedback. So this is some example of what we could do for hardware. And so the last, some perspective for the last component is the interaction component. As I said at the beginning, it's not mandatory somehow to do a mapping one-one with what we are doing in the real world. Like we are doing interaction and we are doing some tasks in the real world. Should we do the same in the real world? There are some options for not doing the same. So we can play with different criteria. First one is the degrees of freedom. So for instance, we can reduce the number of degrees of freedom we are trying to manipulate. For instance, here is this application, we call it Sing. So I don't know if you know Sing. Sing is in Adam's Family movie, the hand that is moving near the Adam's Family. And then this hand, we try to animate this hand using a multi-touch control, so just a tablet. And of course, you have a reduced number of degrees of freedom on the tablet compared to the 3D real hand. And we try to see how we could do the animation of this virtual hand, and it works well. So this is possible also to decrease the number of degrees of freedom, not having the mapping 1-1. Another thing is also we could separate degrees of freedom. This is the case what we did with this example, for instance, where we are using our two hands for manipulating one virtual hand. And in this example, we had one hand that will manipulate and that will receive the global motion of the virtual hand and receive the global forces, and the other hand will control the local multi-finger finger motions. So we conduct user studies by separating degrees of freedom between our two hands, and in fact it works quite well, and we were able to manipulate and do some specific manipulations using this separation between the degrees of freedom of one hand in our two real hands. So we can also play with the sensory modalities. So haptic devices have to be used with other sensory modalities in VR, and visual feedback is, of course, a key component, and we need to think about how we'll have to synchronize the sensory modalities. We have seen that cross-modal modalities, for instance, with the virtual mitten, are also quite interesting, as they could provide, for instance, haptic feedback sensation in addition to enrich our interaction. We can also play with the haptic patterns. So this example I show here. Here you have just a sphere with a multi-actuator inside. This is only a vibration actuator. And then just playing with the haptic pattern and combining this with a visual feedback, then you can have several sensations. So for instance, here you have friction that come here, and you can see. You can have liquid sensation when you are manipulating liquid, and then you have different sensations just playing with how you would like to manipulate haptic patterns. So this is not like a one-one mapping between what you could see and what you could feel. You don't have any physics behind, but you are just having haptic patterns that you link to visual feedback. And we are playing with the sensory modality, but we could also play with haptic modalities themselves. So it comes back to the beginning of my presentation, where I said that we have a diversity of haptic stimuli in real life, and it could be the same also in the virtual environment. So we could manage to have like different haptic stimuli, and this is very challenging, but this is like a nice opportunity for our next research direction, as we could mix different stimuli. Like for instance, here I presented like the tangibles that we could use in addition to middle ultrasound haptics to enhance the interaction. But the possibilities are really wide here because you can simulate different type of haptic stimuli. We have seen in different sessions in this conference that people are trying to simulate and to combine different haptic stimuli, and this is of course really interesting. And here the adventure is really in progress. So this is my final message. I hope that you are now sharing also a little bit of my interest with haptics and that haptics in VR, and I hope we will be able to play all together with the haptic sensation in the next year. So it will conclude my talk. I would like to thank my colleagues and students, and most important, I would like to thank you very much for attending my presentation.
Any question or comments? Yeah.
Hi, David Lindelbar, Carnegie Mellon. Super cool presentation. I love your body of work. So when we look at haptic controllers, right, we on the one hand have all the specialized application where it's super important, like surgical training, medical, robotic control. And then on the other hand, we have end users or consumer part, which is pretty much only vibrotactile. Do you see any convergence where we take the hundreds of haptic controllers that this community, the Sikai communities and others have built, and translating that into something that could be used by millions of users, like actual end users, apart from these specialized applications? So what components could we take and kind of to build this into a form factor that is viable on a larger scale?
Yes, thanks for the great question. Yes, in fact, yes, it is true. When you are looking at the general audience and what we have in terms of haptic devices is only most of the time vibrations. So it's quite poor. Like even like that's what we have here in our community when we're trying to introduce like stretch, temperature, or other type of stimuli. So I guess we have a lot of startups. As I said, in this last decade, we had a lot of startup companies trying to sell new devices, but it does not work a lot. and it does not work a lot just because I guess we don't have the audience for this device or the interest of this device. So it means that it's not sufficient in terms of stimuli that we have, because in fact, I have seen at the beginning when you are like holding a glass, so you have like so many different haptic stimuli just holding a glass that just with one device, even if it's not vibration, that you are not feeling everything. So you need somehow to find device when you are able to combine, so you need to think about locations. So we still, I think it's our work also to still think about where we can put device so that people in the company can then trying to sell more interesting device by themselves.
Thank you.
Who else?
So thanks a lot for the wonderful presentation and for sharing your work. Of course, very interesting work. So I would like to seek your comment, well, for Janendra from IIIT Delhi, India. So I would like to seek your comment on this, do we need physics thing, right? So basically you said already that machine learning can be employed for many things to emulate lots of simulations in the VR, and simultaneously we are talking about do we need physics, and I loved that you said, okay, physics for the rigid body dynamics kind of thing may not be required as such, but for example, in the cases where we really need to model the fluid dynamics and simulate that experience, maybe physics can be more interesting. But I think, what's your comment on, for example, there are applications where we need not to have very accurate experiences of this fluid-based dynamics in VR, right? So for example, entertainment, gaming, and even for cooking for that matter, we don't need accurate behavior of the fluid dynamics in VR. So do you think this AI-based models can be used to understand, we already know the fluid dynamics well, we can use data to, for this fluid dynamics, and then we can use that data to generate experiences in VR to simulate these experiences. What's your comment on that? Thanks.
Thanks for the question. In the computer graphics community, physics-based models now are using more and more AI. I mean, we have more and more contribution using AI, especially for liquids, for instance. For deformable, this is more difficult. I mean, people are still struggling to have like differential equations that could be used for having AI for this type of application. So computer graphics is still struggling to introduce AI for physics-based simulation. So that's the first point. So when it comes to VR, then we really need like to have interactive frame rates. So we come like much higher in terms of constraints that we have at the hand. And of course, this means that we are still waiting for more contribution from the computer graphics community so that we'll be able to achieve this frame rate. That's the first point. And then the second point is that we need data. And when we look at like physics-based simulation and 3D physics-based simulation, and you have like a lot of different material properties in our real life, then we don't have the data for the 3D properties. And that's what we need to collect in parallel to the formulation and the equations.
Hi, Maud. Henry Fuchs, UNC Chapel Hill. Thank you for that very interesting talk. I want to follow up the first question that was asked here about your view of the future as will there be a possibility that these various specialized devices from this large collection, something will emerge that would be useful for the mass market? I wonder if you could think about 10 years or 20 years in the future. Can you imagine anything of new devices which will be mass market enough so all of us can have it?
Yes, thanks, Henry, for the great question. So I guess we had, like yesterday in the keynote, one answer from Meta coming with the bracelet. But on my side, I will say that we have also other opportunities. And one other opportunity I would like to explore is like using our everyday life objects. And we have a lot of different objects in our everyday life. And then maybe we can use them as a different way of having properties and haptic feedback in the virtual environments. So we worked a little bit on that when you are manipulating tangibles. In fact, once you wear a HMD, that you are not able to see your real hand, which means that you can play with the shape of the object, the material properties, without like having people feeling the discrepancy between what you feel and what you see in the virtual environment. And of course, this is quite interesting because we could use our everyday life object without having to like design very, very specific haptic devices and a very complex one, using our everyday life object and putting and trying to understand with the visual feedback or the audio feedback how we combine this together in the HMD to have this haptic device. So I think this is a nice alternative.
Thank you.
One more? Yep.
Hi, Yudai Tanaka from University of Chicago. Very inspiring talk, especially the software part. Really enjoyed. I think related to like these previous questions, I think not directly presenting the feedback directly to the finger part. So like the exact location that the users should feel the sensation will open up the flexibility of the form factor. So like, you know, like people start doing like a relocated device, for instance, to represent the sensation applied to the finger part, but instead applied to the wrist, you know, like the TASB from Meta 5 years ago. I wanted to hear your take on this kind of like compromising approach of realism, but to improve the practicality of the interaction and form factor of the devices.
Okay, thanks for the question. Yes, we have seen this. I guess part of this is this uncoated type haptic device that we have seen, and these devices are able somehow like to redirect like the device. And as I said just before, it should be combined with visual feedback because like we can have retargeting methods and retargeting approach to combine with visual feedback and still having the sensation of like haptic sensation plus visual feedback. For all these devices, this is really like trying to have like this interaction techniques that should be designed is not only the device that we should do, but only we should think about the software and the visual feedback, especially because we are predominant with visual feedback in VR and AR, and trying to see how it works. And then my second comment would be, in VR and AR, we don't have the same constraints. And in AR, we are like struggling with a haptic device that we could see, because we are in an AR scenario. It means that we should be very careful about what type of haptic device we are using, because of course we can see them. And this means that we need to think about how the visual feedback could be used to enhance or to, I would say, to hide or not to hide the haptic device. And this is somehow not exactly the same research direction. So we have like many different research directions depending if we are in VR and AR.
Thank you very much, Maud. I'd like to make some bit different question. It is getting more common and then doable to put the stimuli onto the visual cortex to have some, visual stimulation. So, but there's no single haptic cortex in the brain. But do you see any potential in the far future as an ideal unified to use the BCI?
Yeah. Thanks, this is a nice question. I mean, this is great. I will think like very far.
Very far,
very
yes.
Far.
Are you aware of any ongoing research activities and anything?
Yeah, I think like neuroscientists, when they try to explain the haptics and the sense of touch, I mean, this is very complex because compared to eyes or here, I mean, we have like mechanoreceptor in our whole body. It means that we have different types of perception and we have like an infinite number of solutions for having stimuli. So this means that it's more complex, and of course our brain is trying to integrate everything, and this is not like only one zone of the brain, but like several zones that are activated at the same time. So when you are using eyes, this is a little bit different. And of course it comes to how we could use, for instance, brain-computer interfaces, or maybe another interface that we don't know for the moment, to try to analyze these signals. So we try to do that once. We use the brain-computer interfaces with haptic interface, and we were able to capture some signals. But this is really like preliminary. And then now we should think about like, if we are using this, how it could be useful to integrate and to understand in VR what we are using. Because this is what I also like underline in my presentation. We don't know if we are exactly the same haptic perception in VR compared to what we have in the real life. And then we have to compare. And there are like so many user studies to conduct to understand what is the user's perception in VR.
Thank you for the answer.
Okay, it's the right time to wrap up the keynote session. Meta talk is waiting, so let's thank Maud again. Thanks.
All right, hey everyone. So that was a great talk, Maud. Thank you, and thanks, Untek, for chairing the session. It was great. Just a couple of things. So we'll have now a great talk from Project ARIA from Meta, who are our Diamond sponsors. So I have got quite a few emails from many of you over the last 1 year or so about how we can use Project ARIA, how to engage with them. So they're the right folks to talk about that, and they're going to talk about like what the project is and take you from there. But before the start, I have a quick reminder. So we do not have any special breaks for demos and posters. So demos are upstairs in the Skyview room. So please make your time to go there and engage with the demo presenters there. Right? Okay. Thank you so much. So yeah, off to James and Maddie.
Thank you. All right, I'm going to get set up here. We're going to do a demo as well. Bear with us. We're going to set up for a moment. While we're waiting, who saw the Orion announcement at Meta Connect? Can I get a show of hands? Oh, cool. And then how many of you own a pair of Ray-Ban Meta glasses? Okay. And then who here has tried Project Aria or worn Project Aria glasses? Pretty good number. And then even if you haven't tried Project Aria glasses, which by the way are right here, who has used Aria data from Aria? Okay, great. Yeah, we got a number of folks. Okay, so my name's James Fort, and I'm a research product manager at Meta Reality Labs. I'm going to try to hold this thing so I don't have to. And Maddie Bowen's here with me. And I'm privileged to work with some of the world's leading engineers and researchers in the areas of AR, VR, SLAM, and 3D vision, both in Meta and a growing list of over now 150 academic and commercial partners that use Project Aria. I'll just start off by saying Project Aria is not Orion. Project Aria is not Ray-Ban Meta. It's a research device. It's for researchers internally in Meta, and it's for the external community. And it's clear that Meta is investing significantly in smart glasses and that this area is exploding. Today we're going to talk about the kind of research vision that you can achieve with Aria and what we're aiming for. So what if a future set of AR smart glasses could provide the right information exactly when we need it? Imagine a true personal assistant able to help you in any complex task, able to give you reminders in the moment based on your context. Well, AI is here today, but it's not quite how we just described it. And with new products like Ray-Ban Meta, we're starting to see how AI can be more seamlessly embedded into our ambient experience by asking it questions like interpreting a picture that I just took. And these interfaces are great. And really, most of our interaction with AI today is via LLMs, where we're typing something into a context window, and we're trying to distill everything into this context window. But we can tell that that's limited in a major way. AI systems are only as good as the training data that are used to create them and the context we're able to provide to them when we ask them for things. So I'll start by talking a little bit about the training data. LLMs today are primarily trained on internet data, which is mostly text and images, and they make meaning of the world from the patterns inherent in those data. But our lives are much richer than the text and image data on the internet, and it's impossible for these models to know about us without us supplying some form of contextual information. So what does that mean? That usually means what we're trying to do is condense everything that this LLM needs to know about us in something that we're summarizing in real time as we're trying to input into the LLM system. That has a huge cognitive load, and it's really limited by the number of characters that are available in the context window of these systems. These models have now even started to develop this concept of a memory. You can see if you're using ChatGPT, it says updating memory. And that memory is some context of the ways that you've interacted with this system in the past, such as your preferences and key pieces of information. But that's actually an extremely small signal when we're really talking about all the context that we could possibly be supplying to these systems. And it's still a really high effort for us to codify the world in that way. We reach into our memory and we try to formulate these phrases that really are trying to capture whole days or even months or years of our lives. And for AI to be truly useful to us throughout our daily lives, it needs to be trained and operated from the human perspective. That means we need to train models with data that capture as much of the human perspective as possible. And it means we need to utilize sensors that perceive from the human perspective at the time of inference. Really, what's going on around me at the time when I'm trying to ask this AI system for some relevant information. And the overarching goal of this field that we're engaged in, called egocentric AI, is to try to capture that context and provide it to systems in real time. The human perspective, which we'll just show here in this video, is much richer than a network of text and images. As humans, we walk through environments, we look at objects, we hold objects, and we interact with other people in the environment. We engage in complex mental and physical tasks. For example, we cook recipes, we assemble furniture, we learn a new sport. And how can we capture all that? Can we hold our phone the whole day and just like walk around with the camera on? It's not really practical. Likewise, can we wear a Quest headset all day? Just from weight limitation perspective, it's not really practical. So we need a device to collect human-centric data. And it needs to optimize for two major axes that we've identified here. One, it needs a set of sensors that can collect data on the order of what a human can sense. If you think about all the senses we have to really understand our surroundings, we need a device that has on the order of that level of sensing. And then we need a form factor that we can actually wear. If we're going to capture the context of our day, we need to have a device that can accompany us for the day. So devices like HoloLens or Quest, they have that sensor suite, and they've been used for egocentric research, by the way, but they're just too heavy and bulky to wear for long durations of time. And then on the other axis, we have devices like the Vuzix glasses or the GoPro camera, and those can be worn for a long period of time, and by the way, are also used for egocentric research. But they lack the relevant sensors for this comprehensive view of the human perspective. So we realized that we need to make a move into egocentric research and create a transformational device that can capture elements of our experience in the world to fill this gap. And so that's Project Aria here, which Maddie has. And you can see the device. It's a very lightweight device. If you've come to our booth maybe yesterday or if you come by today, you can take a look and you can wear this yourself. It's about 70 grams. And this is Project Aria. It's not Ray-Ban Meta. It may look somewhat similar in form factor. It's also not Orion. Don't get it confused. This is a product. This is a research product, and it's not a prototype. It's not something that we sell. It's a tool. We use it extensively in our own research internally inside of Meta, and our academic and commercial researchers across the world have been using it for several years now. So what's actually packed in this set of glasses? You can see all of this on our website. Project Aria has an RGB camera. It has 2 SLAM cameras. It has eye tracking cameras. It has IMUs for measuring very precise acceleration and trajectory in space. It has spatialized microphones, 7 of them, for capturing spatial audio. It has various connectivity options like Wi-Fi, Bluetooth, etc. Essentially, it has all the input mechanisms you'd expect on an AR device or future smart glasses. And again, I want to iterate, you can start to think about this as an analogy of all the senses we have as a human. This is a device to capture the human perspective. We use Project Aria internally for many of our research efforts, and we also make Project Aria available to you. We give Aria glasses to limited partners, and we provide the Aria Research Kit, which is a supporting kit of tools and AR-centric algorithms to you. And so that's a kit that you can use to do your own research if you apply and you have a research idea. But we also have something called the Open Science Initiatives. And the Open Science Initiatives are a set of data sets, models, and tools that we provide to the community, where even if you don't have the Aria glasses, right away, today, you can download these data sets and models and start doing egocentric research. Even before you have an idea, you can get a sense of what egocentric data looks like. So we'll give you an overview of both and show you some new things in each of these areas. And I'm going to start with Aria Research Kit and give you an overview and talk through some ways of using ARK and some of the capabilities. And then we're going to do a short demo. You may have seen Maddie sort of moving the glasses around, and that wasn't just to show them off to you. That was us creating a SLAM map in real time to initialize a map for these glasses that we're going to show you a demo of. So if you want to do egocentric research, you not only need a device like the Project Aria glasses, you also need tools to configure and manage the massive amount of rich data that it produces, ways to process the recorded data with AR-centric algorithms that will extract meaning from that data and be useful signals to things like downstream research, and even ways to develop applications in real time. So if you have data streams from the device, you can use those data streams in real time and build things on top of it, like an application that can do some kind of machine learning inference. So the ARIA Research Kit enables you to record, process, prototype, and efficiently consume egocentric data for downstream processes. And it's composed of the device, tools, a client SDK for prototyping, and then our algorithms available in a cloud API that we make so that you can easily access data. We'll start with perhaps the most obvious way of using the ARIA Research Kit, and that's to record data with the glasses. So Maddie, if you could hold those up, you can easily start recording data on the glasses directly by pressing a button on the top right corner of the glasses. And you can record really easily up to several hours of data out in the wild. If you have a battery pack attached to these glasses, which you can easily do, you can extend the recording indefinitely from a battery perspective. And then depending on the profile that you choose, which essentially means which sensors you use in your recording at which frame rate, you can record for quite a long time, even a couple hours on average. And while the recording happens, I just want to call out that we're quite concerned about data privacy in general. There's this bright white light that's running as the recording is happening to let people in your environment know that you're recording. And then we also have a privacy switch. So if somebody doesn't want to be recorded, you can easily turn off the recording and it kills that recording. So we're very privacy first in our research. Beyond just the glasses, on your phone, Android or iOS, we enable you to easily configure and manage your recordings out in the wild. That means wherever you're recording, as you're doing your experimentation, you can manage your recordings. You can look at what you've recorded. You can delete a recording, rename it. You can choose what sensors you want to utilize in your recording, and then easily you can put the glasses on and see a live stream of what you're recording and get confident in your recordings. So we offer all these features directly on your phone. So I'm going to get a little bit into the next use case. So you've done your recording. The next thing you might want to do, you've got these raw sensor streams, eye tracking camera, RGB camera, SLAM camera, IMU. Now you want to compute signals. For example, where were my hands in 3D space? What did my space look like? What are the 3D dimensions of my space? Where were my eyes looking? These signals are the things we enable you to compute. And so we offer something called machine perception services where we house some of our core algorithms and make those available to you so you can upload your data and have things like a SLAM map or hand tracking signals or eye tracking signals processed. This is a video sequence that just goes through some examples of annotations by the machine perception services. And this is kind of everything all in one shot. Given the limited time here, I can't go into all of them in detail, but I just want to show you that we have eye tracking signals. We have a SLAM map with really detailed semi-dense point clouds representing a space. We've got hand tracking signals. So everything relevant to your space and your human experience in the space can be computed by these algorithms, and then you can visualize them. The next thing I'm going to talk about is prototyping. So in prototyping, we have an SDK that enables you to take the live sensor streams, and with those live sensor streams, you can then put them onto your computer and run models on top of them in real time. So what we're going to do is we're going to cross our fingers and switch HDMI cables here to this other laptop that has this running in real time right now. Hold your breath. I know I am. It's okay. It could be going up. We may just restart the viewer. Okay. That's okay. Yeah. So the SDK enables you to essentially stream all the visually relevant data to your machine, And then we offer a visualizer that we build on top of a tool called Rerun, which is an open source visualizer for 3D visualization and other types of sensor streams. And then on this machine, which you can see when you come to our booth later today, we have a live demo that you can experiment with. You can wear the glasses. I'm just going to put them on now. Let's see. We might have to recreate the SLAM map. And when you come to the booth, you'll be able to put on the glasses and see your own eyes in real time and see where your gaze is looking. And then you'll be able to see models that essentially compute where the bounding boxes of each of the objects in the scene are located. Can you put it to the other screen? Yeah. There you go. All right. And maybe full screen it. Yep, perfect. Okay, so the things that we see in this view are a SLAM map, which I think we may have reset the SLAM map, so you'll start to see points that are being computed on the top left. And this essentially represents the space. And our SLAM algorithms are running in real time, and you can start to see features being computed of the space. The other thing that you can see in the top left is the trajectory of the glasses. So I have the very accurate 6 degree of freedom trajectory of the glasses in real time. And what you can see in the top right image, actually first I'll guide your attention to the eye tracking cameras, which are a very detailed view of my eyes. And with these eye tracking cameras, we can compute a very accurate vector of where each eye is looking. And then we calculate the intersection of those two vectors to give you the depth. And so this vector essentially is the direction of my gaze plus the depth of my gaze. So maybe you can notice a difference. It might be tough to see, yeah, if we zoom in me looking at something that's like directly in front of me, or me looking at something in the back of the room, you can see the length of the vector adjusting in real time. And maybe we'll just do a little game here where Maddie is gonna move her finger left and right, and let's see if you can see in the, should be the top right image, me tracking her finger in pretty high time and space accuracy. Great, thanks. So the other thing I also want to call out as we're doing this demo, if you look in the bottom right, we've got a model running, and this model is doing object detection. It's a model called DEDIC, which anybody can download and run on their local machine. It's running on the local machine. It's consuming the sensor stream from the glasses through this USB connection. You could build whatever you want on your local machine using this SDK, consume the sensor streams, and run whatever model you want on this data. We've got an object detection model. You can probably see each of you being detected as a bounding box of a person or something similar. And then in the top right, what you see is the intersection of one of those bounding boxes with the eye gaze. So we've used the SDK to compute this resulting intersection. So I'm just going to, gradually look at a few different people, and you can probably see those different bounding boxes being highlighted. So it's really great that not only can you do offline recording and downstream research, you can also do live prototyping with the glasses. So thanks for doing this live demo with me. Okay, now we're going to switch back. Thanks, Maddie. Oh, great. The magic of computers, great. So we're back on track. So I'm just going to jump into, I know we've only got a few minutes left, and then I'm going to jump to questions. Once you've done recording of the data and you have your recordings and then you've, let's say, processed them, it's pretty easy to work with a Colab notebook if you work in Python to start to consume this data and make sense of it and work through it as you start to, let's say, create a data set. And now I would just want to jump into the open science initiatives. This is like what's available to you right now, even if you don't have the glasses yet. So one of the things that we do is we make a model available to you. It's called Ego Blur. And this model enables you to blur faces and license plates. So if you are creating a data set, you can download this model, process data to blur out any PII, and we suggest doing this if you're recording data in environments where you don't want to have personal data associated with the people that you're recording. And then I just want to jump into 6 data sets that we make available to you. This first one is called Nymeria, and it is a human pose data set. So this data set is essentially a data set that enables you to predict the human pose just from the glasses pose. And we've collected this data and essentially equipped people with sensors, motion capture, and used the glasses pose as an input, and then trained a model that predicts human pose, the whole body pose, just from the glasses pose. This next data set is a data set called ARIA Digital Twin, where we've created a digital replica of an entire apartment down to extreme fidelity, which enables you to have a sort of synthetic ground truth that can enable all sorts of tasks like object detection, segmentation, with very detailed ground truth. We have another data set where we have many, many variations of procedurally created environments that enables you to do spatial AI. And then we have a data set focused on hand-object interactions. This is a core signal for AR, and it's a core signal for any kind of egocentric research. What are my hands doing in space is a pretty good signal for what is interesting to me. So this data set focuses on how hands interact with objects, the action of holding an object and grasping, and it also integrates eye tracking to sort of intersect what my eyes are doing with what my hands are doing in space. We have a data set that captures a broad range of everyday activities, and we want to try to encourage the community to create more and more data sets of this type where we can capture as much of the human context as possible and start to promote this kind of data in our partners' research. And then the last thing that I'll talk about data set-wise is a new data set that we released, which is a collection of over 2,400 highly detailed 3D objects that we have scanned and reconstructed. And this object data set is the highest quality data set of digital twins in the world. Each of these objects has a digital counterpart and a physical counterpart. And this kind of data is very useful for object reconstruction research. And you can download this today as well. So a lot of the data that we have recorded is available in this format associated with Quest called the VRS format. And ARIA has traditionally utilized this format. We now make it possible for you to utilize, with very simple commands, just a few API calls. You can use data for downstream training in PyTorch, and you don't have to get very deep into the VRS format to use ARIA data. So we have some of the data sets that I showed available for download directly in this new prepared format for PyTorch. And we also have some standard evaluation libraries for egocentric data. And lastly, I'll just say that Project ARIA is now on Hugging Face. And we're going to make more and more of a presence here as we release more models and data sets. And one use case, of course, we have many use cases. We have over 150 partners now doing many things. But I thought very relevant for this conference, I was recently chatting with one of our partners from University of Glasgow that's doing a very interesting study modeling social signals across realities. And if you think about how people interact in virtual reality and how they interact in regular reality, there's probably differences in social context and how you might have eye contact and space yourself. And so University of Glasgow, Dr. Julie Williamson is doing very interesting research where ARIA is used as the ground truth in regular reality. So imagine you've got a group of people interacting. In this example, we're using ARIA just to provide the signals like eye contact, what's going on there, how people are spatially orienting themselves, how their hands are moving in communication. So we're seeing some really interesting use cases that we did not anticipate coming from some of our partners in this area. And maybe this is inspiring for some of the work that you do. So I'll just finish things off here today. ARIA Research Kit is available today. Come talk to us at our booth. You can submit an application once you have an idea of what you'd like to do. You can go to our website, and then our data sets are available right now for you to download. You can go to our datasets page and download any of these datasets today. If you liked our demo, come by our booth, and you can try this out yourself. You can wear the ARIA glasses and get a sense for how you would use it in your research. And hopefully we have a couple of minutes for questions. Thanks for your time. Yeah, go ahead. Maybe we need a microphone.
Bruce Thomas, University of South Australia. First, thank you for making the stuff available.
Yeah.
That's great for the community. My question is, what are you planning on having extra sensors on here? And you talk about getting the environment. There's more than just sound and light. There's temperature and vibrations, and then also you're capturing some physiological data, or you're planning on capturing more physiological data to make it better for people to understand?
Yeah, the most I can say is that we're constantly evaluating what form factors are going to evolve to look like. And just keep an eye out as we think through this. So yeah, we're constantly looking at the entire available sensor suite on the market and thinking about what additional sensors could potentially be incorporated in future devices and what that would unlock from a research perspective. Absolutely. Yep.
Hello, I'm Jens Grobert from Coburg University. Thank you so much for making this available and your presentation here today.
Yeah.
I also appreciate that you have a privacy-first approach using a status LED and privacy switch. We touched a little bit on that topic on Benko's talk yesterday as well. I assume that in order to meaningfully train these fundamental AI or large AI models, you will need to scale at some point into the public domain. It will not be sufficient to just do that in private or restricted environments. And do you have a feeling that your current project status will actually enable recording in public spaces on a large scale without generating, let's say, public backlashes like with Google Glass? And if not, what do you think you still need to do to enable this large-scale data collection in the medium or long run?
Yeah, I think Ego Blur is a great first step for us in this area. And one of the reasons we're starting with doing this with individual researchers on smaller scales is to experiment with ways to get to very privacy compliant data sets across different regions that have different requirements. And we want to do this in a responsible way. And so that's why we are starting to build in these features and do it at a project-by-project basis and make sure that we can do it right before we get to the stage of scaling up to larger and larger applications. What I will say is that the Ego Exo 4D data set, which has already been released and is available for a little over a year now, was a very large-scale data set that was created with all these privacy practices in mind. So we're starting to see that scale already achieved, and we just need to be careful about how we take steps forward and start expanding on models that help us obscure the right PII and go forward in that way. It's a great question.
Yeah, thank you for addressing it.
Yep.
Hi, I'm Sarita Adve from University of Illinois.
Hi.
Just two related questions. The first one is you don't have depth sensors, right? And that's like I'm just curious why. It's a huge deal. And second, are you planning to make any of your models open?
Yeah, I'll answer the second one first. It's easier. We already have the Ego Blur model as an open model to use, but all of the data sets that we've released, many of them anyway, we have associated models that we've trained internally and shown as demonstrators, and we're constantly thinking about which of these we may be able to open source as well. And it's a relatively granular decision for us to think through when and how we open source things. We have to be a little bit careful from an IP perspective, but yeah, we're always seeking to open source when it makes sense and when it's possible. So keep an eye open for the kinds of models that we'll be making open as we go forward forward in the future. And then your first question was about depth sensors. We have no depth sensor on the device right now. That's true. We do have stereo SLAM cameras, which enables some level of computation of depth. And then the SLAM algorithm itself does output point clouds accurately in 3D space. And we have some of our researchers now utilizing those point clouds for trying to figure out how to like calibrate depth estimation models. Like there are models out there today called like Depth Anything is one of them, for example. So we're trying to figure out how to utilize this 3D data that we already compute and have expertise in to provide good depth signal. That's the best I can say for that right now.
Hi.
Hi.
Two related questions.
Yeah.
One, from your side, how do you evaluate and rank applications? Like what makes it interesting versus not interesting or valuable to you?
Yeah.
And then related to that, who owns and has access to the data that, say, a university researcher would contribute?
The second one's the most important. It's your data. It's your data for sure. So as you record on the device, the data stays on the device. Then you can, bring it down to your local machine for processing. It's still, entirely on your machine at that point. We offer these algorithms that I mentioned to compute signals. And those algorithms we put in a cloud service because we're basically hosting our IP to compute that stuff. And then when you pass the data to the cloud service, it's just for processing of your data. We don't keep your data. That is not something that we're collecting for ourselves. The only time you would elect to make your data available is if you're publishing a paper, and then you publish your data along with the paper. So that's how you, I saw you pointing somewhere. Let's talk about that offline a little bit. That's a little bit of a sensitive topic, so we're careful about, so now I'll use that as a segue back into the other thing that you asked is, we carefully review all the applications, and we're looking for research that aligns with the future of AR. Definitely, but that doesn't mean that we're limiting our minds to what could be possible. And we get applications all the time that surprise us, that we think are really interesting ideas that would, push the boundaries of what you could do with smart classes, that would push the boundaries of what you can do in egocentric AI. So we're surprised all the time by applications. And what I'll say is that a good quality application is what we're looking for, somebody that's really thought through how they're going to use the glasses, what they're going to do with it, how to take advantage of all the sensors on the glasses. That's the kind of thing we're looking for in an application. And we do scrutinize because we have to be a little bit selective about the partners that we engage with. It's an investment from our perspective. And then, we're a little bit careful around the medical domain and thinking through how we do things in a compliant way and managing risks. So we're still trying to navigate that space a little bit carefully. Yeah, thanks. Yeah.
Henry Fuchs, UNC Chapel Hill.
Hi.
By the way, for you guys, I'm a great fan of this. I'm not getting paid. We use ARIA for several projects in our department. We just got a few more glasses. I'm really excited about this. I think there's a lot of possibilities. Now, the thing that I really would like and want to ask you guys people is that we're interested in a number of our projects on full body tracking from the egocentric perspective, not from just looking at somebody, although we do that also. And so we've been interested in putting downward-looking cameras onto the glasses, and we've done that experimentally.
Interesting.
And we've talked to various people at ARIA about, is there enough interest for ARIA to consider having downward-looking cameras? Because, as we all know, there are downward-looking cameras for hand tracking, and you could get lots of information about where you are and where your feet are. So we're interested in health and exercise and things like that.
Cool.
Is there any groundswell to add downward-looking cameras?
We're interested in exploring the full sensor suite that could be possible in the future. Just because today there are 2 SLAM cameras doesn't mean, we're going to be limited in future form factors. And applications as yours, as you mentioned, like understanding what's going on with the whole body pose, certainly something that we could consider. So first of all, I'd like to connect also, given that you're also using ARIA offline, and talk a little bit more about your use case. You may have seen Nymeria, which is a full body pose estimation work. You guys use that?
Yeah. We use something similar, yes.
Similar to that, great.
Yeah, and by the way, 2-person thing is really useful, we find.
Say it
You
again.
know, if there was two people, two of us,
Yeah.
each of us having ARIA glasses.
ARIA on. Yeah.
When I'm looking at you, I get full body of you, thank you.
Yeah, I was excited to see. Actually, it was the researcher that I showcased doing all this like social interaction study with ARIA using 7 at a time in a group, and they had one of the cool things about it is they time synchronized all the glasses. So we have tick sync, which enables you to time synchronize all these recordings, and so it's really interesting to see what people are coming up with. Yeah, thanks for your comment. I don't know how we're doing on time.
We're done.
We're done. Yeah, thank you so much. I appreciate the opportunity. Thank you.
Thanks, everyone. Yeah. But they will be around, so please feel free to talk to them offline. So thank you so much, everyone. Enjoy the break.